Good evening. This is the day 2 of categorical data analysis. So, first, I discuss what do you mean by manifold classification. Here, instead of dividing the population under consideration into two parts by a simple dichotomy, we may also divide into number of parts by a simple process. For instance, we can extend the dichotomy of the population of men into those with blue eyes, those not with blue eyes, and those not with blue eyes maybe this may be threefold division. One, those with brown eyes, and this is those with neither blue nor brown. Again, we can we can get fourthfold division by adding fresh category those with gray eyes. Okay, that means again we divide these portions into two parts. That is those with gray eyes. Good evening, Shashwat. Please tell your friend to join. And those with neither gray, blue, or brown eyes. Okay. So in that way we can classify this. So this is called manifold classification. So that means I already told you, instead of dividing, that means this is instead of dividing, instead of dividing the population under into two parts by simple dichotomy, that is, these are those are blue eyes, those are not blue eyes. Again, we may also divide into a number of parts by simple process. So this is called manifold classification. So in that example, we not only divide this population into two parts, those with the blue eyes, those not with the blue eyes. We divide those not with the blue eyes into two parts, those with not with the brown eyes, those with neither brown or nor blue. Again, I divide those with neither blue nor brown into two parts, those with the gray eyes and those with neither gray, blue or brown eyes. So in that way, if we classify our population, then this is called manifold classification. Formally, we can define this as our population may be divided first according to smallest heads A1, A2, A. In our example, it is two heads, that is those with the blue eyes, those not with the blue eyes. Each of classes these classes so obtain into T heads that is B1, B2, BT. Again, each of these B heads into Q heads, say C1, C2, CU, and so on. Then this is called manifold classification. So there are S cross T cross U ultimate classes, and the total number of classes including N and the ultimate classes is equal to S plus 1, T plus 1, Q plus 1. And as before, the data are consistent if and only if every ultimate classes ultimate class frequency is not negative. Note that the data are completely specified by S T into U into algebraic independent classes class frequencies. Now consider contingency table. Let let us consider the classification in which the attribute A is S-fold and B is P-fold. Hence, there are ST classes of the type AI Bj, where I from 1 to S, J from 1 to T. Now we can arrange our data in a table as follows. So this is for A attribute. This is for B. A1, B1. This is A1, B1. A2, B2, B1, A2. Sorry, A2, B1. AM, B1. AS, AS, B1. Okay. Ignore the comma. A1, B1. A2, B1. Similarly for V2 or second row, B2, A1. A1, B2. Sorry. A1, B2. A2, B2. AM, B2. AS, B2. BK, A1, BK. A2, BK. AM, BK. AS, BK. VT. This is the last row. A1, BT. A2, BT. AM, BT. AS, BT. Okay. And this is marginal frequencies. This is B1, B2, BK, BT, A1, A2, AM, AS, and AM is the total frequency. And this such table is called contingency table. You can use alternative notation. That is, instead of use AIBJ, you can use FIJ. FIJ means AI, BJ, FI not. This means AI, if not J, this is BJ. Okay. So now we can use, instead of AIBJ, FIJ, why it is required or suitable. Okay. Coefficient of contingency this is the two-way classification of the data is called contingency table. Frequency table is different. We can treat this as a, these are all the frequency, but this classification, two-way classification. If it is one-way classification, then it is the only, suppose if we consider only the marginal part, then it is called frequency table. Okay, you can construct for frequency table for categorical data also, but if there is a two-way classification, if it is one-way classification, then you only use frequency table. Otherwise, if you have more than one-way classification, we present the table either two dimension. If it is two-way classification, three-way classification, we can represent this three dimension and so on. Okay, Shashwato, understood? Shashwato? So coefficients of contingency. Shashwato, okay, I'm telling that because this is a two-way classification, then we need contingency table for representing the joint frequency as well as marginal frequency. But if you have one-way classification, then you just construct frequency table. Frequency table is not only for numerical data, you can also construct frequency table for nominal data, ordinal data, so on. Okay, but there is only one category. If there is more than one category, you need contingency table. For example, if you have two categories, then you can not represent this in frequency table. You need two-dimensional table. This two-dimensional table is called contingency table. For three-way, if there is three categories, okay. Okay, thank you, Shashwat. Now my voice is clear, Shashwat. Please tell me. Coefficient of contingency. The characteristics A. Thank you, Shashwat. The characteristic A is Shuman. So I see you. There are only four who are watching this video. Please tell your friend to join. Okay, I think they got the notification. Please tell them to join immediately. The characteristics A and B are said to be completely independent in the population of large, in the population at large. If for all values remain of remain I think I use S for the level of A and P for the level of B. So I write instead of M for large values of uh, for for large if the all values of S and P, we must have Nij. So this means in K. Okay. So Nij, this is Ni naught, and this means in not K, and this is in naught. So Nij into N naught J divided by total frequency for all I J. And if, however, A and B are not completely independent, sorry, I denote this by F, okay, not N. Please rectify this notation. This is F not N, okay. Please rectify this notation. F not K, sorry, this is F not K. This is F not Fm naught, and this is Fmk. Okay, so this should be Fij, Fi naught, F naught j divided by capital. Okay, so please change this notation. Okay, so completely independent, then and this means if you represent this formal notation, so this should be Am Ai, sorry, Ai Bj, this is Fij, and which is equal to Ai Bj naught. Ai Bj naught means this. So Ai Bj naught means Fi naught F naught j by capital A. Okay, so if A and B are not completely independent, then Ai Bj and Ai Bj naught will not be identical for all the values of I and j. And we define the division by delta ij, which means Fij minus Fi naught F naught j by capital A. So in generally this delta ij not equal to 0 for at least one ij. This means A and B are not independent, otherwise it is completely independent. So first I consider mean square contingency. So these measures are, now we consider some measures of classification. This measure based on delta ij, and first I consider mean squares of contingency. And this is defined as chi square sum of I from 1 to s, j from 1 to t, delta ij square, this deviation, by ai bj naught. This is called chi square contingency. Then the measure mean square contingency denoted by small phi square, which is equal to chi square by capital N, where capital N is a total frequency. We may note that chi square and phi square cannot be negative because both are sum of square, hence it should be non-negative quantity, and hence this can be vanished if and only if every delta number vanishes. That is delta ij by ai, since ai bj not greater than 0, So it should be delta ij equal to 0 for all ij. That means when chi square, when phi square is 0, chi square 0 imply phi square also 0. This means A and B are independent. Now we see that this chi square, which is I from 1 to h, j from 1 to t, del I square by ai bj naught is equal to capital N sum over I from 1 to s, n from 1 to t, is equal to fij square by fi naught minus 1 is equal to t minus 1. I think it's better to write less than equal to n into t minus 1 when just break the actually I write delta I equal to fi j minus fi naught f naught j by n whole square. Just I break the square and get this. Okay, and fi j equal to fi naught f naught j, then when it is independent, actually I mean to say this should be upper bound of this should be n into n t minus 1 when s is equal to t. And therefore, it's pi square, which is less than equal to t minus 1. Okay, so pi square lies between 0 to t minus 1. So please check. Now, that is, this is the limiting value actually, because pi square is I think it is better to write limiting value. And so this equal to give equal to sign, okay, when s is equal to t, and this should be chi square equal to phi square equal to t minus 1. Okay, so hence for this reason phi square is not suitable for comparative study. So since size phi square is a non-negative quantity, so it should be greater than equal to 0, and equality holds. I already mentioned in note 1, A and B are independent. So but it had some limitations. Okay? So now we are going to discuss the limitations. So you should take this thing, okay? This is your homework. Question is why phi square not suitably? Question is why phi square is not suitable for comparative study. Okay, so please complete this and submit. Okay, and the limitations are, since phi square can take any non-negative value, then the limits of phi square vary in different situations. Hence, phi square is not suitable form a coefficient of association. So since phi square, we already see this thing, can take any value any non-negative value, then the limits of phi square vary in different situations. Hence, phi square is not suitable for a coefficient of association. And in T cross T table, so in case of complete association, so that if I naught equal to f naught j equal to fi for all t, and sorry, for all I think it is better to write I f naught j, if not I, because I mean to say, look at the table, if this is a complete associations, then what happened is, look at the table, then this means this part should be 0. Off diagonals are all 0. Off diagonals are all zeros. Okay. So, and S should be T. So, if I represent this in tabular form, then we see that I consider 3 cross 3 table. Okay. So, this is F11, this means F1 naught. Similarly, if we add this, we get F11, which is F01. Similarly, this is for F02 is nothing but a F22. This is F2 naught, which is again F22, F3 naught, because of diagonal elements of 0. So this thing, so in case of complete association, this thing is happening. So hence, for T cross T table, in case of complete associations, so I just consider this part, homework part. Now look at this. Why I am saying I square equal to T minus 1 in case of T cross T table. So if look at this, then you see that if S is equal to T, since S is equal to T, this means it should be, this is sum over J, sum over I from 1 to T, because off diagonal elements are 0. So this should be Fii square Fi naught F naught I minus 1. Okay. So now, since Fii this Fii equal to Fi naught, again F naught I, so this means this thing is cancelled, and how many ones there? T ones. So this should be n into T minus 1. As a result, so chi square equal to n into T minus 1. So this means chi square by n equal to T minus 1. So phi square equal to T minus 1. So see that we can always write this thing. This portion is your homework. Just put delta ij equal to fij minus fi naught f naught j whole square divided by fij f naught j by n whole square, and break this square, then you easily get second part. This is homework, please check. And now since it is complete association, that means all off diagonal elements are 0, and if so this sum reduced to I from 1 to t if I square minus fi naught f naught j minus 1, and since fi equal to fi naught equal to f naught j, so this thing is, this should be 1, this ratio, and hence it should be n into t minus 1. Therefore chi square is nothing but n into t minus 1, hence phi square equal to n minus 1. So you can write this thing for all I, and Fij equal to 0 for all I not equal to j. That is when only the leading diagonal frequencies are non-zero. Leading diagonals means this. These are diagonal, but this is not a leading diagonal. Okay, leading diagonal means exactly Fij elements, Fii elements. These are leading diagonal. Okay, so the third point, the deltas are not algebraically independent. For given I, delta I1 plus delta I2, delta Ij plus delta It, which is sum of j from 1 to t, delta Ij, and we can take that j from 1 to t. Delta Ij means Fij minus Fi naught F naught j by capital N. So this is equal to summation Fij, this is Fi naught minus Fi naught summation F naught j into summation F naught j means capital N by capital N. So this is 0. Okay. So since this is 0 for given I, and this is true for all I, so therefore delta are not algebraically independent. If it is independent, this thing is not happening. So for this reason, there are ST such deltas in virtue of above we have just proved that is this sum equal to 0 for any particular I only t minus 1 of the t quantities the fi delta ij are independent. Similarly, for any j, same process, that way you can show that for given j, only s minus 1 are independent. Hence, in total, number of independent deltas is s minus 1 t minus 1. So, this is the degrees of freedom of this test. If you want to test this, you will learn this thing in higher class in next semester maybe. You use chi-square test. This is the chi-square test statistics. Okay, this chi-square is the chi-square test statistics, and its degrees of freedom s minus 1 to t minus 1. We can same way we argue that there are s minus 1 t minus 1 deltas are independent. So it's the chi-square of s minus 1 t minus 1 degrees of freedom. Okay, so next, and I considered this is called kernel Pearson coefficient. This is a Karl Pearson coefficient of mean square contingency. And we denote this by capital C and defined as chi square y, capital N chi square. In terms of phi, it should be pi square 1 plus pi square. Just divide both sides, both by capital N. Then we get this. As you see that as N increases, if we look at pi, pi should be chi square by N. Then we see that as N increases, this phi tending to 0. Okay. So actually, I want to say, I think it's better to say in that way. So I just consider why I introduce this measure. Suppose the quantity phi, if you look at the phi square, which is chi square by n, and even if we look at that as n tending to infinity, it should be tending to 0, but still this phi square upper bound should be undefined. That means it's tending always greater than 0. So upper bound is it is not possible to give upper bound, it should be infinity. But if n tending to infinity, then it should be, we do not know actually. If chi square is a finite quantity, then it should be chi square is a finite quantity, it should be tending to 0. It should be tending to 0. That means there is a difficulty. One thing is, according to this measure, it should be infinity upper bound, but as intending to infinity, still it is infinity, which is not possible. So for that reason, I considered this measure, which is c equal to root over chi square by n plus chi square. If you look at this measure, then you see that this value should lies between. Uh, it has a some upper bound. Okay. Uh, Here the properties are no sign should be attached to the root, or the coefficient merely shows whether two characters are or are not independent. But in certain case, certain cases, a conventional sign may be used to now look at this. You already see that in T cross T table for complete association, this chi square should be n into t minus 1. And this means the C equal to n into n into t minus 1 by n into n plus n into t minus 1, which is equal to t minus 1 by t. So note that no greater association than the case if phi j equal to phi naught f naught j for all I, and if phi j equal to 0 for all I not equal to j. Sorry, this should be j if not I. Again, this is my mistake. This should be I, if I am. Okay. So hence chi square should be less than equal to n into t minus 1. We already told this thing, show this thing, and this means t should be less than equal to root over t minus 1 by, and the upper limit of C vary for different system and hence it is not suitable for comparative study. Next, property number 3. Now, C0 if and only if A and B are independent each other. And the coefficient, as above, the coefficient has one serious disadvantage, disadvantages, that is 0 should be less than equal to 1, since 0 less than equal to chi square less than equal to n plus chi square. Okay. So the next measure sucrose coefficient. Sucrose coefficient. Even in case of complete association, the value of C is not unity, and its maximum depends on number of rows. And columns of the table. Hence, for remedy, the sucrose propose a alternative coefficient which is denoted by capital T, which is equal to chi square n by root over s minus 1 t minus 1, which is pi square root over s minus 1 n minus t minus 1. And we see that for t equal to 1, in case of complete association, in T cross T table, but it will not be true in case of S cross T classification, when S not equal to T. And this coefficient varies between 0 to 1, 0 and 1. Next measure, Kramer's V square. We see that in an S cross T table, if S greater than T and AI Tj, that is Fij equal to Fi naught F naught j, I think it is better to write FIR. Fii equal to Fi naught F naught j, where I from 1 to t, then chi square equal to n into t minus 1, but if s less than t and if I equal to Fi naught F naught I from 1 to t, then chi square equal to n into s minus 1. Hence, for any s cross t table, chi square is less than equal to capital N, minimum of s minus 1, t minus 1. And Kramer pointed out this, and we may avoid this difficulty according to Kramer by defining v square as chi square divided by n into minimum of s minus 1, t minus 1. This is Kramer v square, and it is clearly see that v lies between 0 and 1. When s is equal to t equal to 2, then v square equal to chi square by capital N, which is equal to pi square. Eventually, v square equal to t square when the table is squared, otherwise v square exceeds t square. Although the differences would not be very large unless s and t varies widely. And also you see that t square by t square is nothing but a, please take this thing, s minus 1, t minus 1, 1 plus pi square. And we can use all these measures for ordinal and nominal data, but now we consider for ordinal string let us consider two jointly distributed attributes A and B. Further some better to write this thing. Let us consider two jointly distributed attributes A and B further assume that the label of each can be arranged according to their degrees of possessions. Here it may happen that as the responses on the attribute A increase towards its high level, its higher level, responses on B also increase towards its higher level, or response or the response of B, responses of B decrease towards its lower level. Such type of association is often called to as a monotone trend association. A pair is said to be concordant pair if the subject ranked higher on A also ranked higher on B. A pair is said to be discordant pair if the subject ranking higher on A ranks lower on B. A pair is said to be tied if the subject have same classification on A and or on B. So now we consider ordinal measure of associations. First I consider Goodman-Kruskal gamma. Let C and D be respectively the number of concordance pair and the number of discordance pair respectively. If the pairs are united on the variable, then C by C plus D is proportion to proportion of concordance pairs, and D by C plus D is the proportion of discordance pairs the difference C by C plus D minus D by C plus D, which is equal to C minus D C plus D, is termed as Goodman-Kruskal gamma. Goodman-Kruskal gamma. And we denote this by gamma. If gamma greater than 0, this means C minus DC plus D greater than 0, that is C by C plus D greater than D by C plus D, this means characters A and B have the positive association and if gamma is less than 0, that is this less than equal to 0, this means this less than this, that is character A and B have the negative association. We see that Woodman-Puskal gamma treats the character symmetrical. That is, any one of them can be taken as response variable. So, gamma treats the characters symmetrically, that is, any one of them can be taken as response variable. And this gamma should be lies between +1 to -1. You can easily verify it from this value C minus D by C plus D is checked. This is your homework. If gamma vanishes, if two variables are independent, but converse may not be true. So that is, if independent imply gamma 0, but gamma 0 does not imply independent. Okay. So we can now we consider another remark, that is, now if C equal to two into sum over I sum over j nij sum over r greater than I sum over k greater than j in rk, and d equal to 2 into sum over I sum over j nij sum over r greater than I, and other is decreasing, that means k less than j in rk, and tk EA equal to number of typed pairs on the characters, on the character A, which is in not N1 not C2 plus N2 not 2 N S not 2. So this is nothing but a sum over I from 1 to S Ni naught into Ni naught minus 1 by 2, since Ni naught is the members, since Ni members, Ni naught members have the same character A. Similarly, TB, which is equal to sum over j from 1 to t n naught j minus 1 by 2 and TAB number of typed pair on both AB which is equal to double summation I j Nij minus 1 by 2. Note that in C2, which is equal to C plus D plus TA plus TB minus TAB. Now we consider the Kendall tau. We know Aij, which is xi sin xi xj, this function defined as 1 if xi greater than xj, 0 if xi equal to xj, minus 1 if xi less than xj. Similarly, we define Bij as sin yi minus yj. And then the measure of rank correlation will be based on the sum is equal to sum over I less than j ai j bij, which is nothing but a c minus d, which is defined as total score. Here we have two choices to make a measure of association. If we wish to standardize standardize is to standardize S to lie the range -1 to +1 and attain ±1 in extreme cases of complete disassociation and complete association. Then Kendall tau, if the first I consider if there is no tie case, then S should be lies between MC2 then Kendall tau is equal to S by which is as a coefficient of association. And clearly whether tau A attain the end point or not completely depends on the number of zero scores. In some if some scores Aij or Bij are zero, the tau A can no longer attain ±1. Now Kendall, this is Kendall tau A. This is Kendall tau A. Now consider Kendall tau v. So the correlation coefficient between two sets of scores Aij, Bij is defined as tau v sum over I less than j Aij, Bij divided by root over sum over I less than j Aij square root over sum I less than j Bij square. So this is the correlation coefficient between two set of scores Aij and Bij. Two sets of scores Aij and Bij. And this is defined as tau A equal to this. And in the presence of tight pair, the measure tau B will be of the form C minus D by root over NC2 minus tau A, sorry, TA. I already defined TA. Yes, I already defined this thing, TA and T. NC2 minus TB. Okay. And note that summation I less than j Aij square is equal to number of pairs I comma j where I less than j for which xi greater than xj or xi less than x. This is equal to NC2 minus number of tie on it, where TA equal to, I already defined this TA, which is equal to I from 1 to S Ni naught into Ni naught minus 1 by. Similarly, we define Bij square as NC2 minus T. And we see that if there are no ties, then tau A equal to tau B, but there are some ties, then tau B should be greater than tau. Note that Rudman-Pascal gamma can also be expressed as C minus D by C plus D. C minus D is equal, this should be unchanged C minus D, and I already find this C plus T as NC2 minus TA minus TB minus plus TAB. It is important to note that this gamma, tau A, tau B all attain plus minus 1 if all the observations are in the cells along the longest diagonal of the table or principal diagonal of the table. Next, I consider the last measure, that is Somade D. Somade's D is a measure of association for ordinal data, and it is defined as D equal to C minus D NC2 minus TA. Is it same as C minus D by NC2 minus TB. In case of complete association, Fij equal to, sorry, this should be Fii. Mistake. Fii equal to Fi naught equal to F naught j for all I, sorry, this is F naught I, okay, F naught I for all I 1 to minimum of St, and all other frequencies are 0. That is, all observations lie in a principal diagonal of table. Then, in that case, S equal to sum over, this should be sum over I less than j, that is number of pairs I less than j, where number of pairs ij where I less than j, that is xi less than xj, or yi less than yj. Similarly, xi greater than xj or yi greater than yj. Okay, so this is I less than j ai j dij, and this equal to number of pairs I j where I less than j, for which xi less than xj or yi less than yj or xi greater than xj or yi greater than yj. Okay, equal to, this equal to number of pairs united on A or B, which is equal to NC2 minus TA or NC2 minus TV. Okay. So hence D equal to one. But all the observations but if all the observations lie on the longest, because I did not use principal diagonal because it is not a square form, that's why. If it is square, this longest diagonal and principal diagonal are same. Of a table such that M Fi is minus I plus 1 equal to Fi naught equal to F naught S minus I plus 1. For all I from 1 to minimum of S comma 2. And all other frequencies are zero. So then S is equal to minus number of pairs ij for which xi greater than xj or y or yi greater than y. And this is nothing but a minus NC2 minus TV or minus NC2 minus TA. So, and then T equal to minus 1. And note that in the above situation, Kendall tau b behave similarly. So this is all about categorical data analysis. So before stopping this topic, please tell me, have you any queries or question? Please, if you have any queries and question, please write in the comment section. I will discuss. And the next day we will start with new topic, scaling of a data. Okay. So please tell me. Please tell me, have you any queries and question? Otherwise, I win this thing. Okay, Shashwato. Thank you. So we'll. Okay, Shuman. Thank you.